And so up to this point, we've been talking about the basic pieces of an operating system. We looked at an overview of the architecture. We looked at how the architecture impacts the design of the operating system. And at a high level, we talked about this idea of programs, and these programs have to share the resources for the operating system. And then we talked about processes, the unit of execution, and we looked at what the parts of these processes are, and we looked at how they impact the system and why you'd use a process. And then we looked at threading, and threading was a lighter weight version of an execution context, and you can have multiple execution contexts in a process. And we looked at how you create these threads and how you remove these threads. And we looked at issues concerning how these threads might interact with one another on the CPU. We looked at the idea of kernel threads. We looked at user level threads, and we considered what happens if you have more than one core on your system. We then looked at scheduling and saw most recently that the way in which you select the next executable context or thread for execution can dramatically impact, either make longer or make shorter, the amount of time that everybody waits on the ready queue. So now we're going to segue and look at another issue concerning what happens when you have multiple execution contexts. Now, synchronization applies equally well when you're talking about processes as well, multiple processes, as well as when you're talking about multiple threads. Okay. So please get the following reading done. It's about, 23, 50, 60, 70, 80, about 30 some odd pages, right? It's very accessible. Please make sure you get the reading done by Tuesday. And it's not my style to give homework over breaks. Next week is Thanksgiving break. And so, at least as far as the perspective of my classes are concerned, I fully expect you to enjoy your Thanksgiving, but I can't speak for my colleagues, right? And that goes back to when I was an undergrad. I'm like, damn you, I'm not going to do any work if, over break. But anyways, enjoy it with your family, and of course, travel safely, right? Safely here and safely back. We want you back safely. All right. So that's the reading. Please make sure you get the reading done. And I am going to post a very small, simple assignment concerning material, more recent material that we've done related to what we're going to talk about today. And that's going to be due on, today's Thursday, on Tuesday. And it's probably going to be like one or two questions just to get you exercised on certain material that we're going to make use of when it comes to the final project. Okay? All right, so please look out for that. I'll certainly send an email through the messaging system on Blackboard. Okay, so chapter 6, it talks about this synchronization. And of course, part of the goal of the chapter 6 is to look at the concepts of synchronization. And we'll talk more formally about what that is, what that means, and why you should care about it. Now, if you never deal with operating systems themselves, and in fact have a capstone student who's dealing with the very problem that we're talking about, synchronization, he's working on the Raspberry Pi, and you'll find out more about the details on Division Day, I guess they call it now, Division Day. But he's having a problem trying to access two I/O devices, a microphone and a camera, on the Raspberry Pi using multiple threads. And so the issue he's having has to do with the fact that Raspbian, which is the operating system for the Raspberry Pi, at least freely available operating system for the Raspberry Pi embedded controller board, does not support kernel level threads. It only supports user level threads. And so one of the problems he's having has to deal with starvation because he needs both audio and video data at the same time. But the problem is that you have that single kernel thread mapped to multiple user threads. It's only two user threads, but because it doesn't support user level threading, if that user thread blocks, all of a sudden the kernel thread blocks on the CPU, right? And so we're working through a fix for some of that. and we only have available the services on Raspbian, which is the operating system. So this idea of synchronization and kernel threads and stuff like that, if you never touch the internals of an operating system, understanding operating systems is very critical to any computer science or IT related profession, because it is the underlying thing, if you will, for all applications that might sit on top. So it talks about this thing called the critical section problem. And the critical section problem is a formalization, theoretically or abstractly, about what the issue is. And certainly there are various approaches that people have for how you solve this critical section problem, right? And critical section problem pertains to the consistency of data, right? And we'll talk about that. And then lastly, it talks about some solutions, right? Some tools and some problems and different ways people have thought about this at a high level. And this is certainly not exhaustive of all methods there are out there, but this is just kind of a high level smattering of us, a small handful, because you could take an entire semester just looking at synchronization, and we don't have the time or the schedule to be able to do that. Okay, so let's take a look. So a process or a thread, you can execute them concurrently, right? And the whole point of multi-programming, as we said earlier in the semester, is to make effective usage of the CPU. You want to keep it busy all the time doing something. Now, certainly when you have multiple cores, you have many CPUs, and you could have many processors, or you could have all those multiple processors on the same piece of silicon on the same chip. You call them multiple cores, right? And so whether it's multiple cores or multiple processors, you want to make sure that they're busy. So you do that by multi-programming. You have multiple processes running, right? And you can have a single application, like a browser, that consists of multiple processes, or you can have multiple threads, right? Or you can have multiple processes, i.e. multiple programs in execution. And so, you could have like Netflix going, you could have your email going, you could have Dropbox going, and all sorts of stuff. And there's lots of other processes that are running that are associated with your operating system, especially if you have a graphical desktop, right? Because there's some process that has to listen for your keyboard keystrokes, listen for your mouse movements and clicks, and also to redraw your screen whenever you press a button, right? You have a click event, and you have to redraw that button in its pressed in form. Okay, and so you have all of these processes running, and they're all accessing data structures. Now, of course, we talked about this idea of round-robin scheduling, which is how most general-purpose operating systems make their scheduling decisions. And therefore, processes and threads can be preempted, because as we had described, when your quantum of time expires, you are interrupted, and so whatever you're doing, you have to stop. And it's now some other process or thread's turn to get the CPU to make some progress in its execution. And so you also have concurrent access to shared data. Now, we saw a very obvious example of this when we had the assignment with the two processes and we did timing, and for that you use shared memory, right? But that was designed very carefully, right? Because one process wrote information to that shared memory, and the other process conceivably read information from that shared data structure. But at the end of the day, you had two processes, process A and process B, and they shared this same piece of memory, this data structure. Now, when I say data structure, I mean something that you put information into, right? It could be something like you studied in data structures and algorithms like linked lists, queues, red-black trees, all sorts of stuff. Or it could just be a block of memory into which you store something, whether it's an array or just a piece of memory, right? And so you have this shared data structure. But what would have happened in that example if instead of process A only writing to that shared memory and process B only reading from that shared memory, what would happen if they could both read or write, right? So let's kind of draw a basic schematic. Hopefully I brought a marker that works. So we had process, it's funny, let me just put that one down. We had process A, and we have process B. And let's say this is RAM, and you have a shared memory segment, shared memory. Process A if you did some timing, right? Process A certainly created process B as a child process, and process A wrote some information into shared memory, right? And so the edge direction here connotes the direction of data flow, right? So process A writes into that shared memory some value. Process B reads information out of that shared memory. Now, that's an easy case, right? Because process A continues to write and process B continues to read. But what happens if process A also reads something and process B also writes something? So then you can get a problem, especially when these two things are executing concurrently. Now, that concurrency can be shared on the same CPUs. Let's say you're sharing one CPU, doing something like round robin. At some point, process A is going to get ready to write something, and then process A gets preempted. It's time to leave the processor. And at the same time, process B gets the CPU. It's on the ready queue, and it's scheduled for execution next for some quantum of time, and it interacts with this shared memory. So then process A comes back again on the CPU, and it thinks that it's picking up where it left off. But in truth, what has happened is that process B has modified something about this, but process A has no idea that has happened. Because from process A's standpoint, this thing is restored, this value, based on the process control block information, which the dispatcher copies onto the CPU when it's process A's turn again. So there's a problem here that can lead to something called inconsistency in your data, right? The ground truth value of what that data structure's value should be is undetermined, right? So there's a problem there. And you can imagine in certain applications like banking, right? You have to know that there's an actual value. It can't be one or the other depending on who wrote first, right? There's a serious problem there. And so what this synchronization deals with are mechanisms that allow or facilitate or mitigate, if you will, this data consistency problem. And you're going to get data consistency problems, sometimes called the race condition, right? Because you have these two execution contexts racing one another to gain access to this data structure called a critical section, right? So that's what synchronization is all about. So if you ever want to write a high scalability, high performance application that uses multiple threads and or multiple processes, you're going to have to deal with synchronization. Okay. All right. Any questions about this? No? All right. So let's illustrate this problem. And that problem that is typical in most operating systems, of course, is all of them, is the so-called producer-consumer problem. And let's recall the producer-consumer problem. You have a buffer, and in this case, it's a so-called ring buffer, right? A ring buffer is just a fancy name for some buffer, like an array. And when you run off the end, you go right back to the beginning again, right? And so you can think of this buffer, instead of being a straight line, as being a ring that wraps back around to itself. So if I drew that buffer like this, instead of straight across, once you reach the end of the buffer, the next place you go is back to the beginning again. So it's called a ring buffer, right? So suppose you have a producer-consumer problem, and the producer's job is to fill the ring buffer. So it writes some value in a location and then goes to the next location, writes a value in that location, goes to the next location. The producer produces information that it puts in this data structure, right? So it's accessing this so-called critical section, and it's going to write information. At the same time, we have a consumer, and this consumer reads and removes information from this buffer. So this consumer is going to be a process that comes along, and it takes information, reads it, and then goes to the next location. So if you have this case of the producer-consumer, you have two processes that are accessing a data structure. It's a shared, they're coordinating through this data structure. One wants to put information there, and the other wants to read information from it. It's consuming data. So if you wanted to provide a solution that's going to coordinate these two, one thing you could do is you could have a counter, right? The producer says, okay, every time I write into this ring buffer, I'm going to increment the counter, and that counter is going to represent how many slots or how many pieces of information it has deposited in that ring buffer, in that data structure. So you could do that, and then conversely, the consumer would take this counter, it would access or read information, consume information from this ring buffer, one entry at a time. And then for each entry it consumes, it's going to decrement that counter by 1. So meaning that, okay, well, I have now consumed one item from this data structure. Now there's one less item that needs to be consumed. Okay? So you can do this with a counter. The producer increments the counter, it's an integer, to tell how many of the buffers or slots in this ring buffer are full. And then the consumer does the dual operation. It consumes or reads out something from the buffer, a piece of information, and decrements the counter because it's reduced the number of stored items by 1. Okay. Any questions about this? Does that make sense? Yeah? All right. So let's take a look at some pseudocode. And this pseudocode we had seen before, and kind of looks a lot like C or C++. We have a while loop, and we can assume that the producer all the time is going to produce something, but you don't want to produce more data than can be stored in the buffer. So what happens here? The producer sits in a tight while loop, and some item is produced that it wants to store, and then it looks at the counter and says, okay, well, if that counter tells me how many of these slots in the buffer are full, right, then I'm not going to produce another one because I don't want to overwrite something that's, or when all slots are full. So in this so-called barrier, right, execution goes from top to bottom, and then it jumps back to the while, beginning and top to bottom, back to the while, open block, and then continues down again. So if execution goes in the downward direction, when it hits this while statement, that while statement prevents that execution from going any further, right? Sometimes that's called a barrier, right? And the condition for that barrier says that if this buffer is full, meaning if I know that I can store buffer size many items in this buffer, and that counter saying the number of slots that is taken is equal to buffer size, that means that the thing is full, right? All of those positions in my ring buffer, in my array, are full. So if that condition holds true, I don't want execution for the producer to continue, right? Because if it continues, well, if you try to write something when something is full, you're going to have to either overwrite or you break something, right? You go out of memory. You go off the end of the buffer, and bad things happen, right? So then, at some point, conceivably, at the same time, right, the consumer is running, and the consumer eventually consumes something, decrements the counter, and at that point, that counter, which is shared between the producer and the consumer, is now less than the buffer size. So once that happens, execution can continue past this barrier. And it's often called a barrier. You'll see that sometimes in documentation and in the literature, because you can think of it as this thing that blocks the further progress of the execution. Now, when you see this, it is still executing, but it's just not doing anything. What is it doing? Well, it's comparing contents of counter to this constant buffer size, which was created through a number sign define, and it's doing the arithmetic logic unit operation to compare values, right? And then what it's doing is saying, okay, continue execution on the same line or the same statement if that is true. The result of that comparison is true, okay? So while progress is not made past this barrier for the execution of the producer, it is still executing statements. But those statements just aren't really very useful, right? Because it's just continually comparing counter to buffer size, comparing counter to buffer size in a tight loop, okay? So any questions about this? No? All right. So then let's say it goes past the barrier because counter is decremented by the consumer that's running in parallel, and it also has access to counter. And then now execution comes down here. It produces the next item and stores it in the buffer at a particular location marked by something called a cursor in. A cursor is nothing more than a number that represents a position or location. And then it increments in, right? So if the counter gets decremented by 1, if in is here, it increments by 1, does modulo buffer size, goes back to the beginning again. So we have another piece of information, counter, which is an integer, and this integer is shared in addition to that buffer. It's shared by the producer and the consumer. And that counter is used by the producer and consumer to manage how many of these slots in our buffer have information inside. Okay, so let's now take a look at the consumer. And remember, these are both executing at the same time. They could both be in different processes, and that buffer and that counter is in shared memory, or they could be two threads. And if they're two threads, threads all see the same data, the same heap part of your program, and this buffer could just be dynamically allocated from RAM by your program, and the counter could just be a global variable, right? And so the consumer and the producer, whether they're two threads or two processes, they're executing concurrently. And here in the consumer, we also have a tight while loop. And what this consumer does, it says, okay, well, if there are any items to consume, then I'm going to continue. So the first thing the consumer does, it has a barrier. And what this barrier checks for is whether or not there are any items to consume. So if there are no items stored in this buffer, stored by the producer, then this counter is going to be 0, and execution for the consumer thread or process will not go past this barrier. So conceivably, while the producer is running concurrently, that producer could produce an element and increment that counter. So now there are no longer zero many items in the buffer, and execution for the consumer goes past this barrier. So now the next thing the consumer does, it uses its cursor out, indexing into the buffer, and it gets that item and does something with it, and then it increments out. So it goes to the next location in that buffer, and the fact that it's modulo the buffer size means that it's a so-called ring buffer. If it currently consumes out being the last item, if I increment by 1, bless you, and do modulo buffer size, I start back at the beginning again. Okay. Any questions about this? Make sense? Okay, so it seems fairly straightforward, but there's a little bit of a problem here. Let's recall what the architecture of a CPU looks like and the relationship between the scheduler and the dispatcher. Now remember, when we talked about process control block and even a thread control block, we referred to the CPU, and we said the CPU has a bunch of subsystems on it. We have an arithmetic logic unit, or ALU, that is responsible for making comparisons, doing logical operations, and so forth. So it's a piece of circuitry at the transistor level in the chip. We have the floating point unit, or FPU, that's responsible for anything that involves decimal numbers, right? So that could be a multiplication, a division, exponentiation, and so forth. And then we also have something called the register file, the registers. And we said those registers are very fast. They run at full chip speed, and they're used for storing intermediate values, right? And then we also said we have something called the program counter. And the program counter stores the address of the next instruction, right? We also had the stack pointer. And the stack pointer points to a region of RAM, has an address, and that is responsible, the stack, for allocating using last in, first out scheme for allocating things like parameters to functions and local variables. And then we also had the memory management. Let's not talk too much about that. So in order to switch your context, you need to copy all of the information that represents a stream of instructions. And so here we have the registers that talk about intermediate values, we have the program counter, and we have the stack pointer, right? Okay, well, if I want to represent the execution of instructions, so let's say I have a function int f, it takes a float a, open, close curly brace, and I have, bless you, I have a local variable. Let's say I have int b equals 7, for example, and I'm adding result return no, if I said result, float, bless you, float result, and let's say result equals A plus B, and then I said return result. So I'm just adding two numbers together, right? Okay, and that should be float. Okay, so if we're going to represent an execution, right, a stream of instructions, the ability to execute things, there are three pieces of information I need. I need the status of the registers, because I need intermediate values. I need the program counter, and I need the stack pointer. So if I put all of these together, that's a so-called execution context. So let me write it this way. I have registers. I have the program counter, and I have a stack pointer, right? So this rectangle here, that's the collection of all the pieces of information I need to represent a stream of execution. When I say stream, I mean a sequential set of instructions that I execute, right? This is called the execution context. Execution context. So now, okay, let's see what happens. Let's focus a little bit on the registers because we haven't really talked much about them. When we compute an operation like float result equals A plus B, well, we fetch a value for A. Well, that's available through the stack because it's a parameter. We fetch the value associated with B. Well, that's also available from the stack because B in this example is a local variable. And then we do the addition, right? So that's arithmetic. Addition, subtraction, logical operations, that's arithmetic. So the ALU performs that. Now, of course, when you add these two together, right, you're going to get a value, right? So if A is equal to, say, 1.1 and B is equal to 7, I'm going to get 7.1. Okay. Now, that intermediate value, 7.1, yes, it is the result of adding A to B if A is 0.1 and B is 7, but that value has to go someplace before you do the assignment, right? Because the ALU is going to say, I'm going to set up a plus operation, and I'm going to fetch a value for A and a value for B. Well, when it fires and it does that plus operation, it has 7.1 as the result. The 7.1 has to go someplace, and where it goes in a register, 7.1. So now, when the equals result is processed, the assignment to result, it says, okay, let me now take this value and push it off to memory someplace on the heap where this variable A is referencing. Okay? So if I have more than one execution context, so let's say I have a thread, right, associated with that execution context, and let's say I have, first, does that make sense? Any questions about this? Yeah. All right. So let's say I have my process control block, and in my process control block, sorry, let me say I have a process list. So here are my processes. And that list has PCB1 for the first process, and I have PCB2 for the second process. Now, when the first process is executing, all of this information for its execution context gets put on the CPU from its PCB. Then, when process 1 is kicked off the processor because it has run for a certain amount of time, then all of a sudden, the current context is saved to the PCB for process 1, and the dispatcher does this work, and then the context for process 2 is now loaded onto the CPU. So if you have two threads or processes that are sharing the same data structure or the same data, you're going to have a problem. Because if process 1 and process 2 do things very rapidly in succession, right? Process 1 is doing something and all of a sudden it's preempted and process 2 is running, you can get improper values. And this is a depiction of that. So suppose you have, let's go back, we have our producer, and our producer increments the counter, counter plus plus. It says, okay, I'm going to take my counter, I'm going to add 1 to it. When it adds 1 to it, it creates an intermediate value. That intermediate value has to go into a register somewhere. And then once it goes into that register, the next thing it does, it assigns it to that variable called counter. So the producer is doing counter plus plus, the consumer is doing counter minus minus, right? So here, when we do a counter plus plus, what's happening is the first thing that happens, and this is the full-blown treatment of it, is that it takes a memory location referred to by counter, that's how variables are implemented, and it loads it from RAM. So here's RAM. I'll just draw RAM really small. And you have a value in RAM, and when you have a variable counter, that is just an address through the linker and the loader that refers to some location in RAM. So the first thing, when you say counter plus plus is the same as counter equals counter plus 1, right? So what does it do? It says counter. Okay, let me take that value in RAM, referred to by counter, and let me load it into the register, counter. If counter was 7, it's going to put 7 in a register. So then you said counter plus 1, right? So it's going to say, all right, well, let me take that register where I loaded the value from counter and let me add 1 to it. So it says, let me take that register and let me do that operation through the ALU, an arithmetic operation. I'm going to add 1. So it adds 1, okay, and then it does the assignment. It says the value of counter is equal to that register plus 1. So then it takes that value, it adds 1 to that 7 in our example, that's now 8, and then it takes that register value and puts it in that location referred to in RAM by the name counter. So this is what happens underneath the covers in assembly language, in machine code, when you say counter plus plus. The dual operation, counter minus minus, is shorthand in your programming language for saying counter is equal to counter minus 1. So what does it do? It does the load of counter into some register, and it allocates a different register. It does the subtraction of 1 from that register, and then it does the assignment of the result to counter, right? So this is underneath the covers what's happening. And part of the problem is that if process 1 is in the middle of doing this, and all of a sudden it's preempted and process 2 is switching, all of a sudden they have different understandings of what the right value is, right? And the reason for that has to do with orderly access to this variable counter. Okay. So in this diagram, let's assume that the counter value is initially 5, ground truth. And then here we have some periods of time. You could think of them as quantums. And given that counter plus plus is this sequence of machine instructions and counter minus minus is this sequence of machine instructions, you can absolutely have, and this is what the assumption here, you have the first process, or S0, executing, and then it gets preempted, and then S1, the first period of time, something else happens, and the next period of time, something else happens. So here, in period S0, well, counter plus plus is executing. So you store from counter to the register, okay, and then you compute the intermediate value. Register 1 gets register 1 plus 1, okay, but it hasn't yet stored the result of register 1 in that variable called counter. It's not done yet. Now, even though it's not done, guess what? These are individual instructions. It can still be preempted. So it has not yet updated counter, the variable. Does that make sense? Okay, so it has an intermediate value in a register. So if it has an intermediate value in a register and it's context switched, well, its information for the execution context is stored off in its PCB. And then the next thing that happens, the other one, its context is loaded from its PCB and it starts executing. So what does it do? Okay, the consumer's executing in step S2 and it takes the counter's value. Now remember, it hasn't yet stored the result of incrementing counter plus 1. So counter still has that original value of 7 at this juncture. So the intermediate value is here, started out as 7. It loaded it, 7. It incremented by 1, so that's now 8. Context switched, so a new process is executing. The first thing it did is it loaded counter, 7. It has no idea that the first process was interrupted in the middle of its operations before it had a chance to do this update. Does that make sense? Okay. Any questions? So let's continue with this example. So the second process comes along and it loads counter, right? And then it decrements by 1. You have an intermediate value. So from the perspective of the first process, it thinks counter should be 8. And from the perspective of the second process, it thinks counter should be 7. Should be 6, right? Because 7 minus 1 is 6. So now, all of a sudden, the first process comes back. Its execution context is loaded, and it says, okay, I have to finish with this last instruction. I'm going to now store in counter's value what my intermediate value was, which was 8, right? Or in this case, 6. Oh, I should have gone with this example. I'm using 7 and 8. But let me start over with these examples. So counter starts initially as 5, and the first process comes along. It stores counter in intermediate register, that's the value in a register. It increments by 1, so it thinks its value is 6. It hasn't yet updated it in RAM. It gets swapped off, and the next process comes. It loads that register. Its value is still 5 in memory. So it takes that value, decrements by 1, thinks it's 4, and then the second process gets context switched off the CPU. The first process is restored onto the CPU. It says, let me finish. So it stores it in the counter. So it takes that memory value and updates it to 6. And then it gets context switched. The second process comes back. It says, let me continue. Let me store. It updates it to 4, right? And so with this particular sequence of instruction execution, at the end of the day, you get 6 and 4. But if you reverse this, it would be 4 and then 6 and end up as 6. So the problem here is that if you did this again and again and again, you don't have a stable value for that counter variable. And the problem has to do with the fact that both of these execution contexts are trying to modify the same piece of information at the same time. And because of preemption and context switching through the dispatcher, you're getting an unstable value. Okay, does that make sense? Any questions? So that's a really, really important problem, and that's called a race condition. And race conditions are fixed by synchronization. Okay, any questions about this? No? All right. So let's take a look at the so-called critical section problem. So let's say we have some number of processes. Now for that example, producer-consumer, I only talked about 2 processes. This problem gets even worse if you have many processes, more than 2. So we have some number of processes, and let's say each process has a so-called critical section. It's a piece of data or data structure that they're trying to access. Now, processes might be changing common variables. It could be through shared memory, or if it's threads, it's just some piece of memory that was allocated on the heap, malloc or new. Right? So you could be updating a file, you could be updating a table, and so forth. So what you want to happen is when any one of these processes decides to interact with this critical section, you don't want the others to be able to access it. Right? Now, in the example that we gave before, how we would have fixed this is the moment that either of these processes were going to do an operation on counter, it should lock out or block the other process from being able to access it. When we had the producer-consumer example before, we had these barriers, and you'll notice here, this barrier said that your execution can't continue. You can't interact with the buffer. You can't read it, you can't write it, you can't increment the counter until some condition is true. It was locked out. It was blocked from being able to do something. So essentially, what this critical section problem says is that we need to have this behavior of preventing other processes from accessing if one process is accessing that critical section, that piece of data. Okay? So the critical section problem is, and this is a poor choice of word in the book, it's not really a protocol, it's a scheme. I mean, you could say it's a protocol in the sense that it's a sequence of doing things, a scheme or recipe or sequence of steps used to achieve some end. But I wouldn't say protocol because that's too easily confused with network protocols. And so here, critical section problem is to design an algorithm or method for how you do this exclusion of other processes if only one process is accessing the critical section. Okay? So how this is done is each process has to ask permission. Can I enter this critical section? Can I use this data structure? And if the answer is no, then it waits a little bit and asks again. Okay, now can I? Kind of like a kid in a car. Are we there yet? Are we there yet? Are we there yet? Can I access it? Can I access it? Can I access it? Yes or no? And the moment it's yes, it only answers yes, this ask function, for one process at a time. So if you have, say, n processes, numbered process 0 through process n minus 1, and let's say if process 1 got a yes answer, that means process 0, process 2, and all the others should have a no answer, and they cannot physically access this data structure. So that means you have so-called orderly access. Only one process at a time can enter this critical section. Because the problem that occurred, we have some critical section. You have two threads or processes. Let's call it process 1, process 2. The problem is that when they executed, they were allowed to be interacting with this data structure at the same time. Now, this at the same time could mean process P1 does this amount of work and that gets preempted. And then process 2 starts doing some work and gets preempted, right? That's a problem because they're both accessing at the same time. And we saw that this counter in that simple example with counter plus plus and counter minus minus, this counter has unstable values. So what you really want to happen, if this is time, and you have access for the critical section, it doesn't matter if process 1 executes it first or process 2 executes it first, but it can't be at the same time. So that means process 1, once it enters a critical section, process 2 cannot touch it until process 1 is done, right? If process 1 gets there first and that request to access the critical section is that the answer is yes, then it executes. Anyone else who tries to access it, they're blocked. They can't access it. If process 2 is the first one to get there and asks, and if it's told yes, it can access it, and anyone else who gets there, the answer to that question, can I access the critical section, is no. So what ends up happening is that you either have process 1 executing the critical section, followed by process 2, or you have process 2 followed by process 1, but you don't have a situation where process 1 and process 2 are executing parts of that at the same time. Okay? All right. Any questions about this? So what we'll get to with this is looking at facilities in the Java programming language that implement something called monitors. But you first have to talk about critical sections before you can get to monitors. Okay. Any questions about this? So if you have a critical section, you have, and this is the standard in the book and the nomenclature they use in the book, you have the critical section, and then everything else that follows that's not critical, they call it the remainder section. Okay? All right. Any questions about this? Does that make sense? Okay, let me check the time. 16. So here's the general structure for the ith process. It doesn't matter what I is, just have some number of processes. So we start out, and the assumption here is something similar to the producer-consumer problem, right? So you're in a tight loop, and you're continually accessing some structure. Okay, so you start out, you ask this question, can I enter the critical section? So they call it entry section, right? It's a question, and its answer is either yes or no. And if it's yes, you can proceed, and you now perform whatever interactions or operations you have on that data structure, i.e. your critical section. So then after that, you have a formal exit command, and the exit is your notification back to the operating system that you're now done with this critical section. Now, the reason for that exit critical section routine is that the operating system needs to be able to tell someone, yeah, all right, you're done, so that I can answer yes for someone else once you're done with the critical section. Okay? All right, and then there's the remainder section. All right. So let's take a look at a very simple approach. And now this is just pseudocode to describe the idea of this notion of a barrier. And this particular barrier works for more than just two processes, right? So instead of saying producer-consumer, you have a large number of processes that are all vying to access this thing, and you're trying to make the access orderly so that one process executes it and then another, but not at the same time. So here we have a simple algorithm. So we're iterating in a while loop, so we're continually trying to access the critical section. And now we have this variable called turn. And turn is an integer. And if turn's integer value matches the same number as the process number or process ID, then that means it's your turn. Okay? So if the jth process, and j could be 1, 2, 3, 4, whatever, if the ith process, comes along and says, okay, well, as long as the turn is not my process number, it can't be my turn, right? So it says here, as long as the turn is j, and j is any number except for I. So let's assume, we had 10 processes. We have process P1, P2, up through P10. And let's say process PI was equal to 2, right? Was process 2, so I is equal to 2. So you're saying while the turn is equal to j. And what does that mean? If it's anything except for me, right? So you could also rewrite this while turn is not equal to 2 if I'm process P2, right? So if it's not my turn, what do I do? Well, I have an empty statement here for the while loop. That's a barrier. So from the perspective of process I, it says as long as the turn number is not my number I, I'm going to stay here, and my execution cannot continue past this barrier, right? Does that make sense? So then what happens, at some point, turn is going to be equal to I, right? So once turn is equal to I, that means it's not stopped by this barrier. Process I can enter the critical section, do something with that data structure, and then it sets the turn to some other number, right? And that means some other process can execute. And so in that case, that means only that process identified by the turn number can execute this critical section. You can't have two processes at the same time because this barrier, this while turn equals j, says if it's not my turn number, then I'm going to sit here and not proceed any further and not access the critical section. Okay? All right. Any questions about this? Does that make sense? All right. So let's take a look at some benefits or properties associated with solutions to the critical section problem. One is called mutual exclusion. Mutual exclusion means that if the ith process, if one process is in the critical section, no other processes can interact with that critical section. That's really, really important because as we saw before, if both processes are in the critical section at the same time, you can get unstable results. And so the idea is to make it so that only one process is executing the critical section at a time. And that's called mutual exclusion. For every pair of processes, only one gets that yes answer as to whether or not it can enter the critical section. And as we saw in the previous slide, one way of achieving that is through a barrier. Because once this turn number is equal to I, that's when the ith process can come through, right? Everything else is blocked because they're stopped at the same barrier. Okay. The other requirement or feature that you need for solutions to the critical section problem is this notion of progress. So Progress says if no process is executing in a critical section, so that means if no one's using the critical section, then that means some process that comes along that wants to access it, that asks that question, can I access it? Eventually, it's going to access it. It's going to get a yes, right? It can't be no all the time, is essentially what that's saying. If there's nobody using the critical section, it's very likely if you ask to use it, you'll be granted that access, okay? Because at the end of the day, all processes have to make progress, right? Or else you never get any work done. So let's take the example where you're trying to write to a file, right? You don't want two processes. So let's say two people are using, say, Microsoft Word, right? And you both are running on the same machine. You both read the Microsoft Word file. One person wants to write it, and then the other person wants to write it. Well, what happens if you both write it at the same time? There's a problem, right? So the answer to that is this mutual exclusion. So that means it's either your version of the document or my version of the document, but not some weird mixture of the two. And then the other thing is that if no one's using that file, if I want to request use for it to open it and change it, then eventually I'll be granted that access, right? That's what the progress means. Okay, and the other one is so-called bounded wait. And what bounded wait says is essentially you're not going to wait forever, right? The amount of time that you're going to wait in this barrier that we talked about before, your progress being impeded before you can access the critical section, the amount of time is going to have an upper bound, meaning that if you wait long enough, eventually you'll gain access to the critical section. There are no infinite waits here, right? And that's an important property because, of course, everyone should be making progress, but at the end of the day, no process should be meant to wait forever. Okay? All right. Any questions about this? Does that make sense? Okay. So in a kernel, if you think about what happens inside the operating system, let's say you're executing a system call. Your program isn't the only thing calling system calls, right? There are multiple programs calling system calls. And so in that sense, there are multiple processes that are trying to access the same data. So let's say you try to create a file. Well, if you try to create a file, you're essentially going to the directory, right? And you're making an entry in that directory. A directory is nothing more than a special object on the file that has a list of things, right? And those things tend to be file names, right? So, or other directories. And so inside the kernel, you have to deal with critical section problem because you have multiple processes that are trying to all access at the same time these shared resources. And these shared resources are associated with all sorts of things like an array of process control blocks, right? The scheduler and the dispatcher, they're both accessing process control blocks. The scheduler wants to pick one for execution. The dispatcher wants to read one so it can copy it onto the processor or store information to it. So the scheduler is reading one, the dispatcher is reading and writing, but they're reading and writing the same list of process control blocks. So there's lots and lots of places in the operating system where you have these critical section problems. And so in the operating system kernel, there are two ways of dealing with this, and the difference has to do with whether or not it preempts or it does not preempt. And so with preemptive, you can be interrupted. You can be kicked off the processor. With non-preemptive, you're allowed to execute to your completion. And once you're done with the processor, you then let the next process have time, right? So in a preemptive kernel, it allows preemption of processes when you're running in kernel mode. Now, if you do that, you have the same problem that we talked about with that counter plus plus and counter minus minus, and you need these synchronization mechanisms. In some kernels, especially embedded systems, you have non-preemptive, so it runs until you either exit kernel mode, so you're done with the system call on behalf of that process, or that particular process voluntarily gives up the CPU. And this voluntarily giving up the CPU is called cooperative multitasking, right? You say, okay, well, I've done enough. Let me signal to the kernel that this is a good place for me to get off the CPU. So you voluntarily signal the kernel for that. Okay. So, any questions about that? The two in the kernel. And this is for kernel itself. This is not user applications. Okay. Any questions? No? All right. So let's take a look at one solution, and I think we'll end with this, 1027, Peterson Solution. And so Peterson Solution is a famous canonical example, and it satisfies these three prerequisites for a critical section problem. It has mutual exclusion, the blocking out of, let's say, one processor, one process versus all the others. It gives you progress, right? And it also has bounded weight. Okay, so this is a good description, and it assumes you have two processes, and it assumes that you have something called atomic instructions. And so that's a new term. An atomic instruction is a specialized instruction, and that specialized instruction has the unique property that it cannot be preempted. So that means this specialized function must execute to its completion, and it cannot be interrupted. It can't be preempted. It can't be taken off the CPU. It's allowed by the kernel to complete, right? And this test and load function, load and store function, is the basis for the implementation of locks. Now, before we talked about these barriers, which were these while loops, but if you think about it, a while loop can be preempted, right? In the middle of the while loop execution, quantum expires, your register file, and all your execution context information is stored in the process control block, and you're kicked off the processor, right? But the basis of this question, can I access the critical section? I'm releasing the critical section. If that question is implemented using these atomic instructions, now you can have orderly access to a critical section without fear of being preempted. Okay? So what do the processes share in Peterson's solution? They share two pieces of information. One is called a turn, right? And that's an integer. And like we said before, if that turn variable is equal to your process ID, right? It's a number describing the process. And in truth, that process ID is nothing more than your index into the PCB table, right? The PCB array, the process control block array. And then we also have a Boolean flag. And remember, this is for two processes. There's the 0th process and the first process indexing into this flag. And what this flag says is it is used to indicate who is ready to enter the critical section. So you have a turn to say whose turn it is, and then this flag says, is this process ready, right? Because the process might not be ready to enter the critical section. Okay, so let's take a look at Peterson's algorithm. And this is from the perspective of process I, right? P sub I. And it doesn't matter what I is. In this case, we have two processes. So the first thing we do, of course, again, we're in a tight loop, and we have the critical section here. And in this green box, we have that question, can I enter the critical section, implemented using Peterson solution. And then below the critical section, we have the signaling that this process is done with the critical section access. And so here we start out, and I says, okay, I'm ready. Process PI says I'm ready to access the critical section. I want to. This is my intent. This is what I'd like to do. And the turn is set to J. All right, well, that means I'm going to give someone else a chance to access the critical section before I try to ask my question. So then what it says, okay, if some other process is ready to access the critical section, and at the same time it's their turn, then I'm going to be prevented from accessing the critical section. So you give someone else a chance to access the critical section, and then you check to see if they're ready. Okay? So accessing critical section, there are two pieces of information. Is this process ready to access it? And at the same time, is it their turn? Now, of course, let's say process J is doing this at the same time. Process J is going to say, well, I think I might be ready. Am I really ready? If it's not ready, then this flag in the J position is going to be false. So if it's not ready and it's its turn, it's going to say, you know what? It's somebody else. Let someone else do it. Okay? So let's say going back to process I, all of a sudden that flag says, oh, well, J is not ready. So that's a false, and it's equal to J's turn. So if J's not ready, then I'm going to go ahead and access the critical section if they're not ready. Because if they're not ready, they're not going to be running, they're not going to be accessing it anyway. So it accesses the critical section, and then when it's done with the critical section, it says, okay, false, I'm not ready to access it. So conceivably, if J is not ready, that meant J was already done with the critical section and set its flag to false. So the criteria now, it's not just the turn, it's if you're ready to access the critical section, okay? And so the basis of this barrier here says that you can only access the critical section in one of two ways. Is it your turn? Yes or no? And are you ready to do that? Yes or no? Both of those have to be satisfied. Well, just one at a time, but both of those criteria will get you access. Okay? Any questions about this? Does that make sense? Okay. And so it just happens that Peterson Solution preserves mutual exclusion, because only a single process at a time can enter the critical section. Otherwise, you're stuck at this barrier asking the question, can I enter the critical section? So the ith process only enters the critical section if one of two things happens. Either it's the ith process's turn, or the flag that says, is the other process ready, if the other processes are not ready, right? So either one of those criteria will allow the ith process to access the critical section. So the answer to this question, can I access the critical section, is going to be yes. If no one else is ready, even though it's not your turn, no one else is ready, so go ahead. Okay? All right. The progress requirement is also satisfied. And what progress says, if other processes aren't using it, i.e. they're not ready, then it still goes ahead, even if it's not its turn. And then the bounded wait requirement is met, because eventually, if it takes some fixed amount of time for each process to execute, even if the others are ready, eventually they're going to say, I'm not accessing it, I'm not ready, right? So eventually, for each of those n-1 processes, the ith one will have a chance to execute, because at some point, all the others will not be ready. Okay? All right. Any questions about this? Does that make sense? So this is the basis. It's still kind of high level, and we'll get into more implementation details of existing synchronization methods, and then we'll have a project that makes use of Java synchronization that you're going to use to compare against the threading example and have it do some real work, and you'll see the difference between the two. Okay? All right. Any final questions? No? Make sense? All right, so it's 10:35. I was anticipating more questions. So we'll stop here, and we'll pick back up on Tuesday with the balance of this module on synchronization. Okay, so I'll see you all on Tuesday.